Let's continue exploring this table, which contains mostly Greek letters. We said the Softmax function has no definite graph. Why so? Well, this function is different. If we take a careful look at its formula, we would see the key difference between this function and the other is it takes an argument the whole vector a instead of individual elements. So, the softmax function is equal to the exponential of the element at position I, divided by the sum of the exponentials of all elements of the vector. So, while the other activation functions get an input value and transform it, regardless of the other elements, the softmax considers the information about the whole set of numbers we have. Time for an example. Let A be equal to xw plus b, which is our well-known model. Then, we can say the output of y will be the softmax of A. Let's look at a hidden layer with 3 units. So, A here is equal to hw plus b. After transforming it through a linear combination, we obtain a vector A with 3 elements, minus 0.21, 0.47, and 1.72. Now, if we used a different activation, such as the sigmoid, we would simply apply the formula for each of the 3 numbers, and we would obtain a new vector containing 3 new numbers. But softmax is special. Each element in the output depends on the entire set of elements of the input. Let's find the softmax of A. First, I'll calculate the denominator. It is given by e to the power of minus 0.21 plus e to the power of 0.47 plus e to the power of 1.72. That's approximately 8. Then, we must divide each exponential by this denominator to get the new vector. The result is 0.1, 0.2, and 0.7. This is our output layer. Okay. A key aspect of the softmax transformation is that the values it outputs are in the range from 0 to 1. Their sum is exactly 1. What else has such a property? Probabilities? Yes, probabilities. Indeed, the point of the softmax transformation is to transform a bunch of arbitrarily large or small numbers that come out of previous layers and fit them into a valid probability distribution. This is extremely important and useful. Remember our example with cats, dogs, and horses we saw earlier? One photo was described by a vector containing 0.1, 0.2, and 0.7. We promised we will tell you how to do that. Well, that's how. Through a softmax transformation. We kept our promise. Now that we know we are talking about probabilities, we can comfortably say we are 70% certain the image is a picture of a horse. This makes everything so intuitive and useful that the softmax activation is often used as the activation of the final output layer in classification problems. So no matter what happens before, the final output of the algorithm is a probability distribution. Alright, this will do for now. Thanks for watching.